for the introduction. My name is Stefan and I'm talking about shear band formation, especially at high strain rates. Yeah, and as I'm talking about high strain rates, a typical application are high-speed impacts, as can be seen on the right-hand side there. And there we have a turbine plate off failure from a rear part of the turbine engine. And after the short motivation, I would like to go on with first with the experiments to understand the nature of shear bending. Next with viscoplastic modeling, but there we can see some limitations. And therefore, I next propose extensions on a non-local formulation. Yeah, both last names are necessary to describe the nature of shear bending. So for the high-speed tests I'm concentrating on, we use very special setup for this high rates, where wave propagation is prolonged through two elastic bars on both sides of the very small specimen. And yeah, for the measurements, we use strain gauges at the bars and high-speed digital image correlation for the small specimen. And for comparison model identification, we also use quasi-static tests at the other edge of the strain rate table. Yeah, typically for top and pressure bar identifications, cylindrical specimens are used. We here use more sophisticated specimens, head-shaped specimens, for shear bending with neo-localization zones. And yeah, then we slightly vary here the offsets between the notches and then get triaxialities around 0. Yeah, with this we get pronounced failure in these regions. And yeah, to show that we have it here to do with ductile shear failure, we had made these micrographs, and there we see this aforementioned shear dynamics. Yeah, further microstructure investigations on EBSD showed refined grain structure by average factor 5. Yeah, this goes well along the hardness increase, which follows the whole patch relation. And yeah, on the right-hand side, we see the thermography measurements where we got a local temperature increase up to more than 400 degrees Celsius. Yeah, very rapid. Yeah, and then surprisingly on our experimental findings was that for the quasi-static test, we got even finer grains. But yeah, there we hypothesize that it's due to the grain growth and further crystallization stages during this cooling phase. Yeah, after this experimental introduction, I'm going on with the viscoplastic modeling next. Here I want to emphasize the adiabatic temperature evolution, which is modeled without the heat diffusion term in the heat equation with the Taylor-Quinn equation. Yeah, and for deformation description, we use the Johnson-Cook model, where all the terms which are multiplicatively combined belong to different physical aspects. Yeah, and the damage is driven by the viscoplastic strain. And in this damage law, triaxiality plays a role, also rate effects and temperature effects. Yeah, and for the damage evolution, we use a more sophisticated approach to standard approaches, which is shown below. Yeah, after the introduction of the model, I now describe the calibration. Yeah, basically you can, in this model, you can distinguish between different tests. Yeah, and some parameters are not clearly defined which tests they belong. Yeah, and at first, so we had to make a split of the parameters, and we just calibrated parameters from the different tests to make it more feasible numerically. Yeah, and then some of the parameters had to be fine-tuned from both tests. Yeah, and in this objective function, both test terms can be seen. And yeah, it can be also seen that we use for many frames global force criteria and also displacement fitting criteria. Yeah, and on the right-hand side, you can see our simulation setup where we shortened the bars to about 10 wavelengths. Yeah, which was feasible for the first wave crossing for the parameter identification. Yeah, and the boundary conditions were received from the strain measurement at the bars. Yeah, now I want to get a bit deeper into this field, digital image correlation identifications. Yeah, and this works. We have this here we have a high localized resolution of measurements for this quasi-static test. Yeah, and then we interpolate the FE results by the TP of the answers function to these points, and then we correlate them. And yeah, just for depiction purposes, yeah, introduce the Shepard method, where we draw a line for this displacement transition. And through this line, I smooth the points around it and circles around it. Yeah, for depiction purposes mentioned. And just for this, I got this more visible diagrams. Yeah, and with this, I see for intermediate points and also for final points, a good coincidence between the curves. Yeah, and also the forces fitted well here. Yeah, same was done for the high-speed tests. And yeah, with them, I have the issue that while I had the quasi-static tests, I had many time frames I could get, as they were quite slow. Here they are very fast. And so I just had about 15, and I had to use all of them, even as we had measurement technology, which had a sampling rate, which was 4 scale orders then of frequency of HDTV. Yeah, and with this, I also received good fitting for intermediate frames. Yeah, here, by the way, here are the frames shown, which I got from in this force diagram. Yeah, and also appropriate fitting for quite finite frames. Yeah, and for verification purposes, I did full-scale simulations. And with this, I got a good coincidence. Yeah, for final frames, there were some slight deviations for damages approaching 1. Yeah, after this identification approach, I give some further information on how we got these models, on the implementations. Yeah, as there was a high strain rate gap between those two mentioned tests, we need both explicit and implicit material routine implementations. Yeah, and especially I want to emphasize here the linear adaptation. Yeah, for the issues for high strain rates with this exponential term in the viscoplastic increment. Yeah, and so we could avoid numerical instabilities. Yeah, also a well-known issue with this viscoplastic model, viscoplastic models this thermomechanical localization, which goes along with a hypervelocity loss in our dynamic case. And yeah, it can be well seen from this force plot and also from this damage fields. And yeah, by viscoplastic modeling, there is a certain internal length still already introduced, but yeah, it becomes very problematic, especially here for high strain rates. And we see plotted over our force plot that it was most problematic here for final increments. Yeah, here I also show for one of the final increments here this approximated internal length scale plotted, where the damage goes from outside to inside, and now inside becomes problematic where this internal length scale decreases dramatically. Yeah, as this is neither mathematical nor physically feasible, I now want to introduce a gradient model, which I showed there, and I use the implicit gradient model approach with another field equation with this Helmholtz equation. And yeah, with this, I also emphasize here for dynamic tests, I introduced this artificial viscosity, which should not change the results or the accuracy of the results. Yeah, and on the right-hand side, it can be seen more visibly that it can be smoothed by giving values to this non-local parameter. And yeah, it was implemented in using this thermomechanical analogy. Yeah, and here I emphasize on one issue that is at this high strain rates with explicit modeling, it's critical to with the CFL criteria that when you set this term very small, the time steps become unreasonably small. Yeah, and to overcome this, I introduced here another viscosity term. Yeah, and then I also did for this calibration with the general goals of mesh independence, yeah, of no hyperbolicity loss and improved incorporation of the fail. Yeah, fitting criteria was similar to before, where here I want to emphasize on the failure time, and yeah, as new criteria on the well-postness criteria, which can be in done by mesh correlation of feasible meshes, or other more analytical criteria like the internal length scale or the zero crossing of the acoustic tensor. Yeah, and with this, just fitting this non-local parameter did not work to overcome this mesh dependence, as there was artificial localization. Yeah, and so also another parameter, this damage evolution parameter, was identified new. Yeah, and with this, I got reasonable results. Yeah, this is the end of the findings, and now I want to come to conclusion. Basically, I introduced a process chain to implement this simulation-assisted split-top pressure by experiments. I had to implement both implicit and explicit material routines. The viscoplastic parameters were identified for a fine-grained field as proof of concept, and was reasonably done until high damages were reached. Therefore, I further had to introduce a non-local model extension, and I provided concept to determine this internal length scale. Yeah, and what comes next is that I also introduced this methodology for nickel-based superalloy. Here I can draw somehow the connection to what I said at the beginning, this air or engine failure. Most of these parts are made of such alloys. And yeah, even for this, it might be more problematic with this ductile brittle transition at high rates. Yeah, and for this, I'm working on a quick phase field modeling approach for ductile brittle transition. Yeah, after my references, I want to thank you for your attention and look forward to your questions.